have a lot of fun. If you are interested in that talk, that's actually someone else from my company, but he did that talk 2 years ago. So if you ping him, maybe he'll share that information still. He's a pretty cool guy. So sorry to let you down, but...
You okay with being streamed?
Absolutely, yep, streaming is cool. So, thanks all for coming out. I know it's late today in B-Sides, and you've already learned so much, and I'm sure your brain is already exploding with how much you've already learned. But I hope you'll bear with me just a little bit more. This is a topic that's kind of near and dear to my heart. So it's RF controls with software-defined radio, sort of blending the two in an investigation. I found that software-defined radio is a topic that a lot of people are curious about, but they don't always necessarily take the chance to go play with it. So I thought I'd kind of cut out the middleman and give you a chance to see what it's like playing around with these controls, how affordable it can be, and just kind of how it's a great way to use the hacker mindset, even if it doesn't directly apply to your work right away. So to get us started, has anyone... Of course my clicker doesn't work. That's how it works, right? Oh, there we go. Has anyone here used a software-defined radio before? Awesome. That's a lot of hands. I'm guessing, but just for fun, who's been curious about software-defined radios but not got a chance to play with them yet? Excellent. That's great. So if you're looking for new projects, if you're looking for fun things to do, if you've been curious about some of the radio research that's come out recently, and it just seems like maybe it's a topic where you'd almost get it, but you haven't gotten there yet, then this is definitely great. There's a lot of signals out there in the world around us. So I do want to stress the air is, well, it's kind of silly to say the air is full of signals, but I like to think of it that way because it's got this magic ring to it. Everything you do, everything you use to communicate these days is over the airwaves in colloquial terms, but we don't really investigate it all the time. So taking the chance to step back and see what's out there, there's this whole world. It's almost like there's signals of different types and different flavors. And you know, they've got different categories and attributes, that some of them are more difficult to understand than others. Some of them are practically legendary. And sometimes I do wonder if we can catch them all. I apologize for the bad Pokemon joke, but not really. There's a lot of Pokemon stuff in this slide deck, so I hope you'll bear with any corniness to come. I enjoy it. For a little bit of an overview for what we're doing today, I'm going to give an overview of RF fundamentals. So some of you might already know, some of you might not, but I'll keep it pretty quick either way. And then we're going to look at how to tune around with software-defined radio that's quite affordable. After that, we're going to look into a few different signals with different tools that I really like that are all free and available on Linux, so you can play around with them without too much investment at all. We'll close by sort of reflecting on the state of RF security and, you know, what makes it tricky, what makes it, you know, maybe something we want to look into more in the future, and what you should do if this has sparked an interest and maybe you want to spend a little more time with this topic. So to get us started, RF all travels as electromagnetic waves. Electromagnetic waves, by definition, all go the speed of light, so they're all going the same speed. The length of the wave is what changes, and that's what we call the wavelength. And based on that, if you have a longer wavelength, then you have a, oh wow, then you have, usually I don't lose on this one. If you have a shorter wavelength, you have a higher frequency. If you have a longer wavelength, then you have a lower frequency. So you're probably used to hearing terms like megahertz or kilohertz. And that's where those terms come in for denoting frequency. Quick way to remember that relationship is that if you multiply the frequency by the wavelength, you'll always get back to the speed. So they're very similar. These are the tools that we're using in our theoretical investigation today. We've got what's called an RTL-SDR. It's about a $30 USB dongle that you can get online. It comes with a little antenna. You plug it into your computer, and that provides all the hardware you need to receive the signals. And then your computer will provide all of the software elements, so that's the software-defined radio part, for processing those signals and displaying it back to you. And of course, when you get the combination of, one would argue anything with open source, you get magic, but software-defined radios plus those tools can lead to some pretty interesting times. There's good tools for Windows as well, but today's just Linux. So let's take our first steps. We're starting out, we're just knowing a little bit about radios and RF signals, and we know they're around, but we don't really know what they look like or where they hide or how they're different from each other. So let's get started with GQRX. I really love this tool. It's super simple. You just fire it up and you can tune your software-defined radio around like you would a normal radio. And you get this beautiful view that's called the waterfall that shows you the change, or it shows you what amplitudes are happening, so what signal strengths at different frequencies. So you can see a big chunk of spectrum, which we call like different ranges of frequencies, and what's happening at different frequencies. So I've got a little bit of a demo to show on that. It is just a video that I've taken, but you can see once you fire up GQRX, you immediately can see what's going on here. The frequency I've got it tuned to right now is 89.9 megahertz, so it's just an FM radio station. And you can see the rise and fall of the signal with someone's voice or with the music. And you've got different filters, a lot of different tools and little settings that you can tweak within there. You can change the gain if you want to make it louder, though sometimes that can get a little bit weird since it's slightly different than volume. You can change the color if you don't like a blue radio signal for whatever reason. And you get the opportunity to, you can type in new frequencies to look at. Maybe I want to listen to a different station, or maybe I want to tune around. I can pull the bar back and forth and see what else is at frequencies nearby if I'm just sort of looking around different spaces of spectrum. So now I'm going to look at some AM signals. The RTL-SDR cannot reach traditional AM radio frequencies, but it can reach frequencies that you might be familiar with if you've ever listened to, for instance, a police repeater scanner or a scanner for repeating police signals. So some signals that are communicated right now, if they're not critical, usually critical signals will have a higher level of security, but you can find conversations people are having for business purposes, or if someone's on patrol or something like that, up in around like the 470, 480 megahertz range. So here I've just tuned around. You'll notice I'm not really seeing anything yet. Sometimes you have to go back and forth because people aren't always talking like on the radio. They're just kind of, only talking when they have something to say. So here we finally picked up some signals. We found it. We've gone to this weird area of frequency that we're not familiar with, and we've found signals. If I was using audio, which I'm not today, you'd be able to hear, maybe someone's calling in a patrol situation, or they're just saying that it's really boring that night. I don't know. That's their business. So for a little bit more of, going backwards, There we go. So for more of an overview of the spectrum in general, this is generalized. This doesn't show everything, but it's just kind of a sense of what lives where in the world of, the safari of signals, where they all live. So at the lower range, we've got the AM radio signals that you're familiar with. The next band, like region of bands up, is anyone an amateur radio operator? Just curious. I've got a couple. So 10 meters all the way through 80 meters is in that band that I've outlined. So if you're used to speaking with other people over long distances using your own radio equipment, that's why you'd be an amateur radio operator. And it's a pretty fun hobby too. Moving up from that, we get into what's called the very high frequencies. So we have television frequencies, we have FM radio, which is a bit more compact than AM radio because of how it's communicated. You'll also notice that I've got some white boxes there. And those white boxes are where the control signals that we're looking at today all hide. So everything we're looking at is within those little stripes. You might notice it's all around like the ultra high frequency range. And that's because it's good for near range communications, because it is a shorter or a higher frequency and a shorter wavelength. There's more details to that, but I won't get too in depth. I'm sure everybody is familiar with the Wi-Fi, so we get up into the 2.4 and 5 gigahertz, and a lot of cellular communication is around there as well. Zooming in on those white boxes that I had, these are the exact ranges that those tend to live. So why these ranges are significant is that the top 4 ones, you'll notice I wrote ISM there, that's industrial, scientific, and medical. So if you have equipment that you want to develop and you need a place to let it operate, but you might not want to get it FCC licensed since it's a very long process, this is a slice of spectrum that your device is allowed to operate as long as it's within the rules for that section, which is basically your device just needs to accept interference if it gets interference. It can't do anything nasty. You know, if something sends it the wrong signal, it can't start jamming everything. So just sending lots of weird signals. So there's those 4 ISM. We've got 433 megahertz, 915 megahertz. We've got, 2.45 and 5.8 gigahertz. And you'll notice I'm referring to them all by the center frequency. So there is a lower and an upper bound to each of these ranges. And devices, if someone says a device is at 433 megahertz, it might not actually be there. It might be a little bit above, a little bit below. It just means that it's generally in that range. And then the last slice I've got is what's called 315 megahertz, and that is an unlicensed area of operation for various devices. So great, we know where our controls are going to be. A little bit about how they operate. We have amplitude shift keying and frequency shift keying, and these are just super simple ways of saying 1 and 0. So if you're used to, having like a voltage change for 1 or 0, here we just have a signal difference. So for amplitude shift keying, it's just based on the length of a pulse. If you're familiar with Morse code, it's kind of like that, but for bits. So you have a short pulse here for a 0 and a long pulse for a 1. And then below that, it's the exact same data, but with frequency shift keying. So we have a lower frequency for our 0 and a higher frequency for our 1. This is our first mystery signal. Does anyone want to guess our mystery signal? Sure, go ahead.
A power switch.
A power switch.
Like
That's pretty much it, yeah. So I use it as a light switch. This is just a super simple RF controller. I'm lazy. I don't want to get out of bed every day to turn my lights on and off. Maybe I just want the lights on and stay in bed. Do that sometimes. And they've got these controllers on Amazon that are super cheap. So I don't have to pay for fancy home automation or anything. But I'm kind of curious, how do these work? Are these actually secure? Can I trust that you guys aren't all going to come around my apartment and just turn the lights on and off and on and off at 4 a.m.? I don't know. Let's find out. So I'm holding this controller in my hand, and I'm like, well, I can see it. I know what it is, but I don't really know anything about it. How do I discover information on this? And it's almost like I wish I had an encyclopedia or some kind of like a signal dex. That would be great. And just kind of point it at the signal, say, tell me what this is, tell me what it's saying. And it would say, oh yeah, I got that, and just translate it for you. It would be so cool if there was a tool like that, wouldn't there? So I looked around, there actually is. It's amazing. There's a tool just like that. It's RTL-433. I'm a huge fan of this tool. It's a command line tool, and it will scan around various frequencies and tell you what it finds and decode them into 1s and 0s. Sometimes it has little profiles as well that other people have made so it can decode the signal a little bit more. In this case, I just used it with the dash QA. So the dash A is to look around, and the dash Q is just making it be quiet, so it's an easier demo. And you can see I've pressed the button there, and in that box I have the signal that I've gotten back. In video, it looks a little bit more exciting. So I've started up the tool, and now I'm pushing the button, and you can see I've got the signal back. I've got something else in there, which is, I'm going to disregard that because that's not when I push the button. And then, yep, looks like when I push, the 1 on or something like that, I get the same thing back. If I push a different button, I get that one. Some of you might be noticing these signals look the same every time. Interesting. So since they look the same, I figured, what the heck, let's map them out. Let's call this a very simple reversing exercise. It'll be fun. So just arbitrarily, I'm going to line up all of the commands for when I push the different buttons. We've got lights 1 through 4, and then turn everything on and turn everything off. And we've got an on and off for each. And lining them up, I've inserted some spaces based on groupings that I think look significant within here. So the first 10 bits are always the same. So that must be either, hey, I'm a remote, or hey, I'm this remote, not somebody else's remote. Listen to me. And then it seems like for all lights, we've got 1 bit set up. For 1 light, we've got a certain thing, and then we've got almost like an ID for which switch should turn on. So which outlet I've got. So is it outlet 1? Is it 2? Is it 3? And then the on and the off change. So we've got like a 0011 for on and a 1100 for off. So now we can sort of translate this into a sentence. When I push the button for a specific, if I'm going for 2 on, I can see what bits mean. It's saying this is remote and, whatever its name is in binary. and turn switch 2 on. So as simple as it might seem, this actually is signal reversing. So we made it. We've gone from something I was holding in my hand and I had no idea what it was, to saying, when I push this button, this happens in this way. And it's always the same signal every time. So again, those of you with a sort of a hacking security mindset might have already noticed, this is definitely vulnerable to replay attacks. So if someone wants to come by with this signal and just sort of play it over and over again, yeah, I'm gonna have a pretty bad night. It's our second mystery signal. And I know, it's so mysterious, you can't even tell what buttons it has or what it does. Does anyone want to guess? It's a fan? That's actually perfect, yeah. It's a fan, amazing. So this is a fan remote. It's got more buttons. It's a little more complicated. You can turn the light on and up and down in different percentages. You can make the fan go different speeds. Cool. So I tried running RTL-433 on this. I'm like, all right, I've got this figured out. This reversing thing, pretty cool. Just push a button, get the answer. Nah, didn't work for this one. So RTL-433 will only, with those options, give you things at 433 megahertz. We don't know what frequency this is at. So we could tune around with GQRX, but it's still got limited features. Maybe we want to have a different view. Maybe we want to see, once we find the frequency, how the signal is changing over time without the waterfall. We want to see the ones and zeros a little more clearly. And maybe, you know, we're ready to step out and start using tools that let us make our own radios almost, our own software-defined radios to run, so that if we ever want to build something that can transmit, we're ready to do that, or give it different views, all kinds of exciting things. So to kind of line them up next to each other, GQRX is a tool that runs using GNU Radio, which is sort of the libraries and the functions that support all of these tools. And GNU Radio Companion, which we're about to use, is something, it's a visual tool that lets you line up blocks and then create your own software-defined radio to run. So I love it a lot. I think it simplifies a lot of what could be complicated about this, since there's a lot of math you have to abstract in decoding those signals. So I've set up a simple GNU Radio Companion file for this. And you can see way over on the left, I've got what's called a GUI slider, and that's kind of like a variable. We've declared this variable of what frequency we want to look at. And since it's a slider, when we hit play and it makes the radio for us, we'll be able to pull the slider back and forth and look at different frequencies. You can't actually see it in the other blocks here, but wherever the 300 megahertz comes up, for the frequency we've defined, that is, I've actually typed in the settings for that block to use that FREQ GUI slider instead. So it's using that variable to know what frequency it should be looking at. We've got the RTL-SDR source, which is very important. This is basically just a chunk of code that says how to handle signals from the software-defined radio we're using. And then we've got the fast Fourier transform sync. So that's kind of like what we were seeing before in GQRX. It shows us the amplitude of different signals or different frequencies across a range of frequencies. And then this thing we've got down below is new, this GUI scope. So this shows us the change in amplitude over time for one frequency, whatever frequency we're looking at right now. And this might give us, you know, a little bit of a better idea of what's going on than just looking at, you know, up, down for all the frequencies. So I've got this set up, and when I press play, I get something like this. In order to tune this, I have to make the scaling a little bit more reasonable. So I'm going to zoom out a lot, first of all, so we can see both a bigger range of time and we can actually tell a bigger range of amplitudes where it doesn't look quite as jumpy. Once I've got that done, I'm going to turn on the peak hold, which is kind of nice. It shows you what the peak point of a signal that's been seen at the frequencies you're scanning is. So if something jumps up and we miss it, we might see it down there. And now I can just kind of pull along with the GUI slider, change the frequency to see what's happening, where our fan thing is. In the background, I'm sort of mashing one of the buttons on the controller here. And there we go. It seems like we've got an area where it's pretty strong. And you'll notice on the bottom there that that peak is coming closer and closer to the middle of the display as we shift the frequencies over. So that's pretty cool. Once we've got this centered, what I like doing is zooming out so we get a better view. Right now it's still pretty jumpy, honestly. All we know is that it's on and it's off. It looks pretty chaotic. So once we zoom out, you can start seeing that some actually look a little bit longer, and some look a little bit shorter, and a little bit more, and now we can almost see the whole signal, the whole message that this controller is sending coming across as those amplitude shift keying 1s and 0s that we had. So I think this is pretty cool too, but I think a lot of this is pretty cool. That's why I'm sharing it with you. So just to kind of recap on that, in my eyes, that 1101, that's what I'm doing. You can see them coming in. We've got a shorter pulse, that one's a 0, longer's a 1, and down below we've got the peak for that signal. So we could sort of do this thing. I'll push every button and write down all the 1s and all the 0s, but if we go back and think on it, we've kind of accomplished what we originally set out to do, which was to find the frequency that this controller lives at. Now that we know where it is, where it's talking to the receiver, we can just use RTL-433 again, which I love. We can make it do all the heavy lifting. So with -F, you can specify what frequency it should look at. And here I've specified that it should look at the center frequency that we sort of found our peak at before. And you'll notice it will decode similarly those 1s and 0s that we were seeing coming across the screen before and save us a lot of work. Now, I could go into some details on how I decoded this one, and it was more complicated. But because of how many different buttons were on this controller, I'll admit it was a little bit more tedious, even though it was still really interesting and a great way to build a new tool. So I thought I'd spend the rest of the time looking into one more mystery signal that I found. So this is all just me rummaging around boxes in my apartment and seeing what RF controls I have. And at the bottom of one box, dusty and lost from my move from Los Angeles, I found this mystery signal, which I'm sure none of you can tell what it is. Nobody knows what this is. That's not a car key, no. And if anyone wants to try and duplicate said key, go ahead, the car's long gone. So, excellent. Let's look into this. People like cars, right? Cars are cooler than fans, cars are cooler than light switches, and sometimes car hacking comes up in the news, we get all excited, our cars are gonna get stolen. Maybe I can, if I still had that car, maybe I could break into my own car. I would not break into anyone else's car, that would be a bad thing. So investigating this device, if we do a little bit of searching, we find that most car control, lock unlockers are going to be at 315 megahertz. So we can just put that right in for RTL-433, and we'll see that as we push the unlock button, we are getting codes back. But for this one, I'm always pushing unlock, and I'm getting different codes. So this is not a case of cheap light switch from Amazon level of hacking. This is a bit more complicated. You'll notice the beginning kind of always looks the same, but after that it changes up, and we might have to do some more investigation. So I did some investigation online to see if anybody else had looked into this. There actually was some great research last year that was done that showed the key distribution methods for this specific controller to be unfortunate. That's a good word for it. And then additionally, the encryption methods for some of these controllers are not great. The device manufacturer said that for new versions of encryption, they're satisfied with the level of security on it. We all know how that goes. It's a work in progress, right? So as a field that fewer people look at, sometimes it can take a little bit longer to get traction on those conversations. But anyways, there's the car key. Interesting. And while I was investigating this, I also noticed there's another flag I hadn't been paying attention to, which is not using the ones I've been using the whole time. So if I remove that -A flag, which is just kind of a blind investigate everything in the area, it'll actually load all of these profiles that people have developed and contributed to the project. So weather stations and maybe other keys and tire pressure monitors, which have been a really interesting topic as well in the past. And kind of an interesting privacy question sometimes as well. And if you look up here, just while this was not me going out looking for TPMs, this was just me sitting around being like, on a Tuesday night, getting signals for this. And I happened across this Toyota tire pressure monitoring system reporting back. So there's some pretty interesting signals out there in the wild, and I didn't expect to find this. So, we've still got a lot of things sort of lurking in the tall grass, as it were, in Pokemon terms. So at this point, we've left our hometown. We've investigated several different signals along the way. I feel comfortable that I understand at least 3 controllers in my house, sort of. Maybe 2 of them. The third one, the car, I couldn't, immediately understand that, but it's still really interesting, and I found some good research to look into if I want to keep investigating this in the future. So we've kind of reached, at this point, the next steps, and the doors open, you think the game's almost over, and then there's so many more battles ahead of you, but they're glorious battles, and they're great battles, and you'll remember them for the rest of your life, and what you learned from them. So in short, I think my takeaways from this were that securing RF systems can be really tricky. The computers that run these sorts of things, if I'm holding a computer that tells a car to unlock, we can't really expect it to have the same level of encryption as a modern computer, which is, much beefier, right? It can do more computations. It has more battery. It doesn't have to live for years and years and years and years without getting new power. So it's difficult. That's not saying that it gets a pass, right? But it is saying that maybe we need more people thinking about how to solve these creatively and looking at new channels that don't already have documentation. Well, sometimes they do, or sometimes they just have less, but just sort of taking those adventures and stepping out of the comfort zone to see what's out there. Things are slowly improving, like in many fields that are still trying to catch up with the rest of modern, what we'd call modern security. But it always helps to have more eyes on those problems. And I think especially when we're developing new solutions, curiosity is so important. If you think in an open-minded way about a new problem, you might not find a solution. But you are going through those thought cycles, and maybe you will come up with something. And maybe you might say something to someone else, and they'll say, hey, I didn't think of it that way. And that could start something. So I think it's important to play around and see what's out there, which that is probably why I chose all of the Pokemon illusions. This is fun. Hacking is fun. So I hope that you would agree with me in that. If any of this sparked your interest, I've got some more resources. So that paper that I mentioned on the VW encryption is up in the left. That was at Usenix Security, and that full paper is available. Also, if you're new to software-defined radios, a lot of the techniques I approached, I really have to say thank you to Michael Osman for. He has an amazing series of courses on this up on his website for free, and he's a great explainer and teacher. Sammy Kamkar is also known for having tons of fun with radios. So if you want more of the fun angle, his Ding Dong Ditch system was great. And he also had a recent DEF CON talk about car hacking, actually. If radios in general are something you're curious about, there's decades and decades and decades of knowledge in the amateur radio scene, and they are always so eager to pass it on to the next generation. There's things that you won't be able to learn commonly in books or without, squinting at math for hours, or you could ask one guy who's just known this his whole life and is very happy to give you the answer. So that's a great thing. And then lastly, if you're picking up things in your house and you're getting curious like I am, there's the FCC ID search. So a lot of the times you'll see, FCC ID, whatever, whatever, whatever. That means there's information tied to that ID. So you can go and type it in, and it'll tell you, probably around what it operates, what the device does. This is also a really great tool for OSINT. A lot of the times if people are less familiar with registering to the FCC, they might put too much information about their product in there. So if you're developing something new, if you're reversing something and it's got an RF element, you might be able to find some great information there if you get stuck along the way. And you can also see what's coming out on a day-by-day basis. So that's all I've got. If anyone has any questions, then please feel free to ask.
We have a few minutes for questions, if there are any questions.
What's the next thing you're going to try and decode?
I think next, I'm not even going to look at SDR for a little while. I think it's super interesting, but I also have one of those new Furbies that came out a couple years ago, and there's been some really interesting research in that area too, so I want to go play with the toys in that. That's what I'm going to do.
Were there any good pages that had, like, you know how you could list, there's a trunk, right? So if you're listening to, like, say you're at a hotel, and you're trying to listen in on, you could decode that, like there's like a
Oh, so
encryption.
trunking of signals?
Yeah, like something, they had something at DEF where I didn't get in, but you need 2 radios at that point, right? So you need one for the trunk, right? Isn't there?
I'm going to go with, I probably know about as much as you do at this point on that topic. I don't want to tell you anything super authoritatively, but I would definitely encourage you to either find the recording and let me know so that I can know the answer to that in the future, because I'm curious about it.
They were doing that for their talk at DEF CON, listening in on like the grounds people and everything. And
yeah, and there are a lot of common communications that are unencrypted.
Well, they were. There was a rolling. Yeah, they were giving out the piece to decode it. So it was encrypted. It was known how to decrypt it.
Yeah, thanks for bringing that up.
Very cool.
In general, as well, within the GNU Radio Companion, there are a lot of decoders for common protocols. So speaking less to eavesdropping and more if you run across a signal that you're not familiar with, that might be a good place to look. Yes?
While you were on your signal safari, did you see any other mystery signals that were surprising, like the TPMS? Like, was there anything else that like came up that you didn't expect?
So the question is what other mysteries I saw in my signal safari. I saw a lot of mysterious signals. So I saw things that might have been, like digital monitors of oil. When you ask me that question, though, I think about how I got started on this. So what got me into hacking was my original signal safari. When I was a kid, I used to tune around all the time, and you could hear amateur radio operators talking, you could hear planes landing, and you could hear something called numbers stations, which used to be how communications would get from somewhere, who knows where, to some people who needed to hear a message in the field somewhere else, who knows where, maybe spies, maybe not. And if you've never heard one of those, a numbers station, and you're looking for something really intriguing and creepy to look up, I'd definitely give that a shot, but that is probably the most mysterious signal I've found on my safaris.
Is there a reason that you didn't include shortwave on your spectrum diagram?
So the question is why I didn't include shortwave on the spectrum diagram, and the reason for that is for these purposes, I wanted to make sure that we covered the controls that we were looking at and sort of the Wi-Fi and the cell signals people are familiar with, down to the AM signals that people are familiar with. So to that point, there are a lot more signals outside of the range that we talked about today even. So I definitely encourage you to think outside the bounds of what I've presented you.
So if we had like your light switch, for example, you showed how easy it would be to do a replay attack with that because of how it's the same signal, but how easy would it be to actually get like an SDR that transmits and actually retransmit that?
The question is how easy it would be to create the replay attack that I talked about on my RF light switch. The answer is very easy. There are lots of projects on GitHub for specifically that light switch. They're usually by enthusiast home automation folks, so they don't think of it as a replay attack. They think of it as, awesome, I can do this with a Raspberry. So it's pretty easy to do. Yeah, Yardstick is also a really good point. There are other software-defined radios within the price point of maybe about like what, $100, $120? The Yardstick is known as one of them, and basically the cost will go up based on what range it can cover, how wide its bandwidth can be at a given time. I think those are the big ones.
Yeah, I had that light switch, and what you can do is you can find out the specific frequency, and after you figure it out, you can buy the radio for it for like $10 or like $5. The little board that does that specific frequency range. So
that's really interesting. I didn't know that. So just
Yeah.
to repeat that comment, I think everyone can hear it, but the radio specific to that remote controller is available for about $10, and that's another great way to replicate a replay attack.
Can we do the same attack on wireless mouse? Like record and then replay it near a company vicinity?
So question about would it be possible to do a replay attack on a wireless mouse? These days, I'd go with probably not, unless it was something that you found that was like a very, very old wireless mouse from a strange corner of the world. And this just kind of gets into how each device handles its communications. So wireless mice handle their communications in a very different way. There are vulnerabilities for those sometimes. In the recent history, I'm thinking of what was called like the click jacking or the mouse jacking attacks. So those are, valid vulnerabilities. They're just not, the standard record and replay vulnerabilities.
Would it be possible to amplify and catch signals from keywords, eavesdrop on keystrokes for this thing?
So the question is eavesdropping on keystrokes with software-defined radios. Does that sound accurate? Okay. So when I think of that, I'd think more towards what's called like a side channel attack, unless you're using a wireless keyboard that's vulnerable. So if there's a wireless keyboard that's vulnerable and you're within range of it, or if you have what's called a directional antenna, so you can sort of catch a little bit of a signal in a specific direction and then amplify it enough to translate it, and that keyboard were vulnerable, then you could potentially recover data from it. On the other hand, if you just have a normal keyboard, there have been some really like crazy off-the-walls research into like electromagnetic fluctuations of a keyboard as someone presses a key, and potentially that could lead to something, but it would probably be very, very specific conditions that you'd need to operate it.
Anybody else? All right, so I guess let's thank you.
Yeah, thank you for the questions.